Good afternoon, everyone, and welcome to the Parsons Technical Webinar Series. We're excited to have you all with us today for the first webinar of 2024. We have a great lineup for the year, and we're happy to have with us today Jim Schutz and Taylor Schweigel to kick off 2024. Today, they will be presenting on the fractured bedrock characterization, a case study implementation of the Parsons Bedrock Matrix tool. A few housekeeping items first on the next slide. So during the presentation today, we'll be keeping all phone lines muted until the Q&A session at the end to keep background noise down. If you have any questions throughout the webinar, you can put them in the chat feature at any time, and we'll answer them at the end. This webinar today has been approved for one professional development hour credit, or PDH. If you'd like to get a PDH credit, you can download the form about your attendance. There are a few multiple choice questions to be able to get PDH credit. I will be posting the link to that form as well as the questions, so you have a guide for what to look out for during the presentation. And if you have any issues getting that form, please let us know and we'll get it to you after the webinar. This webinar is being recorded and will be available on the Parsons YouTube channel in the next few days. So just a brief agenda for today's webinar. First, we'll introduce our guest speakers, followed by a core value moment. After that will be the technical presentation, and we'll wrap up at the end with Q&A session. So a little bit about our two presenters today. Jim Schutz is a principal hydrogeologist and technical director of environmental geological services at Parsons. He has over 24 years of experience specializing in groundwater modeling, investigation, and remediation of sites in complex geological environments. He earned his BS and MS from the University of Buffalo, and he's a PG in both New York and Pennsylvania. Taylor is a geologist also at Parsons, who specializes in advanced field data collection techniques, bedrock structural geology, GIS, as well as data visualization and dashboarding. She earned her BS in geological science from the University of Rochester and her MS from the University of Buffalo, specializing in structural geology. She also spent a year abroad as part of her studies and is also a club volleyball coach. And with that, I'll hand it off to Jim for the core value moment.
All right, well, thank you, Jessica. So at Parsons, we have 6 core values, and before every meeting, we like to discuss one of those. For today's presentation, we're going to talk about quality, and a subcategory of quality, which I think is one of the most important aspects of good quality, is communication. So a couple of tips for good communication, and like I said, communication is one of the key aspects of high quality work, and I think we can all agree good communication is effective across many different aspects of the projects that we work on, the the deliverables that we come up with, and the client services that we provide. So a couple of good tips here. Consider your audience. Sometimes you'll be having internal team communications. You'll be communicating with clients, subcontractors, regulators, property owners. You may have mixed communications, whereas you have a lot of these different groups in the same communication stream. You really need to tailor your message, tailor your communication for the audience that you're communicating with. Proactive listening. So proactive listening, I encourage everyone to look this up on the internet. There's a long list of things and information that you can provide that are provided related to proactive listening. A couple of things that I think about when I discuss proactive listening is really, absorbing the information that someone is presenting to you and thinking about it, not just simply waiting for a moment and a break in the conversation so that you can interject, like actually listening, And sometimes you don't even need to respond. Sometimes just the fact that you're listening is good enough for the communication. Some 5 C's for good communication: be clear, be correct, be complete, be concise, and be compassionate. I think clarity is one of the most important aspects on this list of 5 for me, because I see a lot of miscommunication happening when we're just not being clear enough or being direct enough sometimes. Also, use the right platform. So I think we can all admit that there are plenty of platforms for us to communicate with, and some of those platforms are better for one style of communication or one topic of communication, and others are better for something else. For example, you might be in a Teams message, in a chat message with a team member through Teams or some other chatting platform, and you might need to at some point break that into an actual verbal conversation, or maybe an email is more appropriate. So think about what you're trying to communicate, adapt when you need to, and use the right platform. And for that, we'll now get into the technical presentation. So yeah, thank you all for joining. This is a really great topic and something that I really get excited about, and that is fractured bedrock and fractured bedrock fate and transport of contaminants. Today, we're going to talk about, well, first we're going to talk through some fundamentals of understanding fractured rock and what really led into this matrix tool and this sort of the background development of it. I'd like to have an educational component, like a real solid educational component in these presentations, something that might be in a college course. So we're going to talk a little bit about stereo nets. We're also going to talk about this pretty interesting and fun test that you can do in open boreholes called the bore fluid replacement test. And then we're going to talk about the Bedrock's matrix decision tool itself as an overview, and then show how we used this tool on a very specific site. So we're nothing without our team. So the support from the Parsons team has just been great, and I'd like to give a shout out to Heather Budzik, our project manager, Richie Inklema, our project geologist, Matt Krantz, our engineer, and Jim Makovchik, another geologist. So the approach, we're originally tasked with the idea of, okay, there's a lot of fractured rock references out there, but we need sort of a Cliff Notes version of them. So Parsons, can you distill this down into, a tool and some reference guidance information so that as managers, as regulators, as folks that may not be geologists or might be new to a fractured rock site, they can get up to speed fairly quickly and evaluate the site for the tools that are being used and the aspects of the fate and transport that are really relevant to the purpose of that project. So we basically coalesced a large body of reference material, and a few of those references, which I highly recommend you go to, ITRC, that's the Interstate Technology Regulatory Council. So they have a really great fractured rock website. ClueIn, that's cluein.org. It's another great resource for environmental remediation. In this case, they have a whole web page dedicated to fractured rock. And Midwest Geosciences Group, another great entity that provides real-time courses and courses via video conference that are recorded. So we can go through some of the fundamentals to understanding fractured rock in this next section. And this puzzle piece concept is from ITRC, so I want to reference that. Probably noticed on the previous page. Within the puzzle piece of a conceptual site model, i.e. fate and transport, there are 3 main fundamentals that we break down. That's geology, hydrogeology, and biogeochemistry. So these are interlocking pieces because not only do they all need to be considered in your conceptual site model for fractured rock, and really for most media, but fractured rock, there are nuances that we'll discuss today. But these puzzle pieces are connected in a way because they overlap in how they affect one another. You can't really talk about geology without talking about biogeochemistry. How does the rock affect the biogeochemistry, and or vice versa? And you can't really talk about the hydrogeology if you're not considering the geology and not considering the biogeochemistry. So we do split them apart into 3 fundamentals, but we recognize how that they overlap and they interconnect and interlock, as you see in this puzzle piece. A few important concepts that we'll go through today. You'll notice that we use multiple tools for each fundamental. You'll notice that we talk a lot about high resolution data collection methods, and we talk a lot about discrete fractured network models. So that's where you don't think about the rock block itself, you think about the discrete fracture where groundwater is flowing, and that's what you're mostly trying to characterize. You got to understand the effects of matrix diffusion, you got to understand the effects of primary porosity, but really honing in on the fracture, the discrete fracture, and where that groundwater is flowing is what we're going to talk about. So under geology, we want to consider the rock type. Is it sedimentary? Is it igneous? Is it metamorphic? Depending on which type of rock it is, for example, in a sedimentary regime, you probably have horizontal bedding planes that are primary conduits of flow, essentially. Whereas igneous and metamorphics, those have been, those rocks have been formed under much different situations, and the stresses that have been placed on them are usually what causes the fracturing. So, here, for example, this might be an igneous or metamorphic, and you can see how the fractures are not horizontal at all. You need to consider the matrix effects as well as the fractures themselves. And what we like to do is really try and find two components to study when we're thinking about geology. Outcrop, while especially in the Northeast, we don't often have the opportunity to have outcrops, but that doesn't necessarily mean there is no information to be gained. It's important to kind of look through the research, look for, there might be a mine nearby, like an open pit mine that you can get access to, and look at the outcrop there, or in this case, near a lake bed, the rock of interest was outcropping, and you get an appreciation of the vertical fractures and the strike and dip of those fractures. And of course, the rock core itself. So second in the fundamentals is hydrogeology. Within fractured rock, I think we can all be aware that there's somewhat extreme heterogeneity in the hydraulic properties, and that really plays out into some of the math that I'm going to show here. For example, transmissivity is the product of hydraulic conductivity and aquifer thickness. So oftentimes we're analyzing for transmissivity, and we calculate the hydraulic conductivity by the aquifer thickness. So that means you take B here and it moves over to the denominator on the other side of the equation. So let's think about that for a second in terms of discrete fracture networks. So if you have this fracture block, and then you have these tight fractures, and let's say, these are a hundredth of a foot, or, maybe up to 500ths in fracture aperture. That's a pretty tight zone for water to be flowing in. If you're calculating T, and if you're measuring T, let's say a slug test or something, and then you're going to calculate K by dividing by B, what is your aquifer thickness? Sometimes people might use the screen length of a screened well and use that as B, or you might have information that says the unit is 80 feet thick. Okay, so if I take 80 and I move that over to the denominator under the T and get a hydraulic conductivity, that's going to be a much smaller number than if I take the zone that is actually flowing, which, the aquifer in here, if this matrix rock is pretty low hydraulic conductivity and this is where all the flow is happening, you got to think about what you're assigning your value B, i.e. your aquifer thickness. And then, so that's hydraulic conductivity. We talk about storativity in this image over here. Storativity is kind of a hard concept to understand. It's similar to porosity, but not. It's actually the volume that comes out of the aquifer based on a unit of drawdown and a unit of area. So it's really related to how much water do you get out of an aquifer based on the drawdown. So you can see how there it's associated with porosity, but it's a little bit different because it's an in-field measurement based on pumping tests. And when you have a tight fracture, again, like I showed in the previous depiction, you can really get an appreciation of there's just not that much water there. And that really affects how much you're going to need to pump if it's, let's say, a pump and treat. How much are you going to need to inject if you're going to do an in situ biogeochemical in situ remediation, for example. We also need to think about fracture interconnectivity. How do those fractures align vertically, horizontally? In fractured rock, we often have plume channeling. So, in these higher permeability zones within a fracture itself, you might hit that zone or you might not, and that might change what your characterization looks like. Talk a little bit more here about the effects of porosity. Just from a straight mathematical basis, you can understand how important porosity is. When we're calculating the average linear velocity of the groundwater, which is associated to the contaminant facing transport, that equation is hydraulic conductivity times gradient divided by porosity. So porosity, two examples here, a porosity of 20%, i.e. 0.2 for, let's say, a sand or some other unsaturated zone, versus a porosity of fractured rock, which is oftentimes definitely less than 10%, less than 5%, can even be less than 1%. So you can notice, because these values are less than 1 and they're in the denominator of the average linear velocity equation, that's going to have a dramatic increase in average linear velocity when you decrease the effective porosity. So this is a factor of 20. If you're calculating your average linear velocity and you say, okay, I'm going 1 unit in 1 unit of days, I'm going 1 unit in distance in 1 unit of days at 20% porosity, but then the effective porosity is really 1%, that's a factor of 20. So you can see how much more dramatic the plume, or how much more farther the plume could extend based on low porosity. Third, we're going to talk about biogeochemistry. So we really need to think about depth discrete groundwater samples for environmental delineation, isolating those fractures, sampling from those fractures where the water's flowing, and making sure you're not sampling multiple zones. Natural attenuation is part of the biogeochemical piece of the puzzle, general water quality, and of course, microbial populations for in situ remediation. This image here is of a local dolomite in Western New York called the Lockport dolomite. And I love this image for a couple of reasons. One, so this is a real high flow zone. We could tell exactly where we were at on this project in the aquifer, because we would lose water, no return, hundreds of gallons into a single fracture. And it's also of high permeability because it's a dissolved gypsum seam. So this is a dolomite, it's an evaporite deposit. You have a gypsum seam, which gypsum is an evaporite, and it's calcium sulfate. That calcium sulfate dissolves, obviously break apart the calcium and the sulfate, and now you have all this sulfate in this small fracture zone. So we have really high concentrations of sulfate, which is directly related to bioremediation, because as you're probably aware, sulfate is you need to get into sulfate reducing conditions in bioremediation of chlorinated solvents in a reductive environment. So you need to understand your sulfate, and you need to kind of overcome it because it's an electron competitor. Fun fact here, this is also within a stromatolite. So a stromatolite, those are the first microbial populations on planet Earth. They terraformed planet Earth. Before stromatolites, some billion years ago, Earth was a anoxic, toxic place for life, and the first microbes, these stromatolites, they produced oxygen, changed the ocean into what we know today from a very reducing acidic condition, and produced the atmosphere that we breathe. So it's kind of fun doing bioremediation right in a stromatolite deposit. So anyways, we're going to get into some fundamentals now and talk about stereo nets. So stereo nets, and I'll have to admit, even a lot of geologists are intimidated by stereo nets because they don't necessarily get taught all the time, and they're a very, very nuanced statistical graphic. So yeah, they're intimidating. They're even more intimidating when they're bright pink and they look something like a random AI generated Death Star prototype or something. But we're gonna simplify that, and you guys will all understand stereonets at the end of this presentation. Um, so what is a stereonet? The stereonet is a graphical representation of strike and dip of a fracture. So in this case, with this very simplistic graphic that I got from an educational website, we talk about stereonets, and essentially the stereonet here, this round circular net, we have north at the top, south at the bottom, west on the left, and east on the right. This is a lower hemisphere stereonet. And what you see graphically are poles, those are the little black dots, and planes, which are the circular arcs going around this stereonet. So this is the bottom of a bowl, essentially, and a fracture running through that bowl, as you see on this very simplistic graphic here, where we have a ceramic bowl, something out of someone's kitchen, and we have a CD, a compact disc, which in the past, we used to listen to music and store data on these. Now we pretty much hang them outside to scare away birds and animals. But anyways, we have this disc and it's sitting in this bowl. And going through the disc in the center is a magic marker. So this disc represents a fracture plane, and where this disc outline contacts the bowl, if you drew your magic marker line on that, that would be your plane on the stereonet. You see on the image B here, we're looking down at that plane. And then the pole is the vertical marker, and that marks the opposite side of the stereonet. And so you have poles and planes. Poles and planes are a little bit redundant. You don't need to plot both of them. I like to plot both of them because they help me understand what I'm looking at. So here we have a collection of poles and we have a collection of planes. And from that, we know, aha, this very particular fracture, because I've reduced the information down to one fracture, is dipping in the north-northwest direction. So up in this direction at a slight angle of 15 to 20 degrees. Rose diagrams we also look at, those are a little more intuitive, and you can see the orientation there. So we put this into three-dimensional model, and then we're able to do a discrete fractured network approach to identify where we want to drill at this particular site. Well fluid replacement testing. So this is a really great test that at Parsons we've developed, and we've been able to very efficiently self-perform this test. That's what I really like about it, is we can do it efficiently. Our geologists in the field can complete the test, get an understanding of the fractured rock setting themselves. And so what this test is we pump tracer in at the top and we pump well water out of the bottom. And in doing so, we replace the water, and then we look for the groundwater to come back into the open borehole. So a little graphical depiction of this, very simplistic. So here you can see we're pumping tracer in, and because we're pumping out of the bottom, we have the pumping rate set like exactly the same. So tracer's not going out into the fractures, or groundwater's not flowing through our tracer field. We replace the borehole fluid with a tracer. This tracer can be DI water, or it can be slightly saline, depending on your regulatory environment. And you got to work with your regulators on that. So keep this image in mind as I go to the next slide. Again, this is the bottom of the casing. This is the open borehole. We've replaced the water in it with a tracer. So that's the image on the left here. Now we've identified where a fracture is. We don't know yet because we haven't done the test, but we have a conductivity probe that we're going to run up and down in our open borehole. On the right-hand side, you're going to see a graphic that represents what the output looks like. Depth or elevation aligned with this open borehole, and higher to lower conductivity on the right-hand side. So we start running our probe up and down, and we get like a baseline. So it's all low conductivity here. In this case, I'm sorry, this is all high conductivity. So this is a slightly saline tracer. And then over time, you can see natural groundwater starts flowing back into the open borehole through the fracture. Again, we're running our probe up and down as the natural groundwater starts to migrate through the open borehole. You actually see a little pick of conductivity, and then you see that continue on in time. So each one of these lines represents a succession in time, i.e. another up and down movement of the probe. So that's the bore fluid replacement test, something that, again, I think is really a great depiction and gives accurate data on where the flow is happening. And with that, Taylor?
All right. Yeah, so Jim's given you a good baseline here with the fundamentals, and we're going to start talking about the Bedrock matrix decision tool itself and the reference guide that we developed using those fundamentals, keeping those concepts in mind. So our Bedrock matrix decision tool was basically, we wanted to, like Jim said, make a Cliff Notes version of all of these great resources that there are out there, make it easy to digest for people to make decisions about sites and evaluate their characterization through data collection techniques, and also evaluate remediation strategies for Bedrock sites, and give people a baseline to make sure they have enough data and the right kind of data for their site. And this is site specific. So this tool is obviously, it's made with a broad sort of range of topics and with a broad audience in mind, but you do really need to make sure that you're thinking about it on a site specific level, and not every tool within this will fit necessarily with your site. But within this tool, there are three main components: a state geology overview and some regional geology quick reference guides. These are both New York State centric because we developed this tool in and for New York State, and also the decision matrix tool itself to help you guide investigation. So the first component in terms of New York State geology includes a summary table. These are broken out by physiographic province. We thought that was a good way to sort of group things. Similarly, we have primary and secondary bedrock types for you to get an overview of what kind of rock you'll be seeing here likely, important structural trends or features, hydrogeological features in the area, if there's any special features, if a shear zone or a special fault is really important to this physiographic province, we want you to be able to have that name right off the bat, and important units within those physiographic provinces, be they based on just rock type or actual named formations or groups. And also we included counties and then New York State Department of Environmental Conservation, DEC regions here. So if you know where your site is, both what county it's in, what region it's in, you can easily look up what sort of physiographic provinces you might encounter there, and then take a jump forward and see what kind of rocks you'll have there. This New York State overview also includes a generalized geological history of New York State, focusing on the bedrock and not all the really cool superficial deposits we have here as well. And then this map that we developed using a couple of tools from the New York State Museum's GIS repository that we've supplemented and refined a little bit, with a generalized bedrock geology broken out by igneous, metamorphic, sedimentary, and also the New York State brittle structures map that we've supplemented with some additional structure data showing faults, fractures, lineaments, all that good stuff. You can also see on this map, we have those physiographic provinces. So when you're looking at your table, you have an idea, am I in the Allegheny Plateau, the Catskill Mountains, etc. Second component, and this was my favorite part, were these regional geology quick reference guides. So for each physiographic province, we made a guide, and this is like the essence of these cliff notes for each province. They include an introduction, which is kind of the 10,000-foot view of each region, and also includes things like if there's specific geomorphology that's interesting, that's not necessarily bedrock geology. We do include then a section about bedrock geology, structural geology, and bedrock hydrogeology. We also include all of the references that we used in the development of these, so you can go to those primary sources and read the information yourself and really kickstart your desktop study, and then find papers from sort of that academic lineage as a jumping off point. And because this should be multidisciplinary and it should be accessible to people anywhere from scientists to stakeholders, we include a glossary as well for a lot of the geological and technical terms in here. We want you to be able to understand this document so you'll be able to use it. And then the third component is our Bedrock Matrix decision tool. This is basically for a qualitative assessment of how you're doing with your site characterization so far. And this is broken out into categories. You'll recognize the fundamentals that Jim gave us a great overview of: geology, hydrogeology, and biogeochemistry there. And then we also specifically called out conceptual site models, CSMs, and then the design remediation components, because they really intertwine those fundamental concepts and need a standalone category. And the template we were given essentially for when we were developing this was like the red, yellow, green, stop, caution, go sort of idea. And so we used those categories to qualitatively basically say, like, red, either you don't have information or you need more investigation. Yellow, you have some investigation, you have some good data perhaps, but maybe you need more of it spatially across your site or higher resolution data in a specific area. And green, meaning you have a really comprehensive high resolution data set in order to work on the characterization of your site. So the matrix consists generally of questions. These questions are about those fundamentals or CSMs that you're going to ask of your own site. And then we have answers. So you're going to ask those questions of your site. You're going to come up with the answer based on those questions. And then you're going to see where your answer fits here. Is it more red, yellow, green for that specific question? And use that as a way to both evaluate qualitatively how you're doing in terms of your data collection and your strategies, and also as an idea of what more can you do if you're not satisfied with that current data set that you have. Some example questions from this deal with hydraulic conductivity, the potential for back diffusion, dealing with natural and man-made features, considering both of those in your characterization, and also something about like where to put your well screens if you're doing screened wells in Bedrock, that sort of thing. And these call back to our fundamentals again. And you can sort of see that these fall into certain categories, or some of the tie-dye ones, they rely on more of our fundamental categories as well. All right, so now we're going to take you into our site example. The site is in upstate New York, and because that's a big place, we're going to give you a circle here to kind of narrow you in a little bit on your focus. And let's get you introduced to the site here. All right, so the site is within the green rectangle in the aerial photo on the right there. It is down gradient from a former manufacturing facility. It has a shallow water table, and Bedrock is really actually close to the ground surface. The primary contaminants of concern are chlorinated volatile organic compounds in Bedrock. There's possible DNAPL, and it is adjacent to a surface water body, as you can see on the right-hand side there. We're going to show you a little bit how we walked through the desktop study, some previous investigations, and then how we're going to use our matrix tool to help guide our own investigation and how we chose to characterize the site. So this is again our map from our first component. And generally we can see that we're dealing with sandstones, siltstones, and shales, primarily sandstone with some interbedded siltstone and shale from that. We also had some good information about the structural geology from research that was done not too far from this site. You can see rose diagrams similar to what Jim showed earlier. These are actually showing strike instead of dip direction though. So rotate yourself 90 degrees and then you'll be on track for these. And this shows two predominant fracture sets in this area for subvertical fractures. And that includes a northwest set and an east-northeast set. The image that the point is on now is showing a fracture survey done in a surface water body offshore nearby the site. And it again shows the east-northeast fracture set and then a northwest to north-northwest fracture set. So consistent fracture sets here. We were also fortunate enough that there was some previous investigation at the site and also just up gradient of our site. This included core and overburden borings. It included core discrete fracture network or core DFN analytical results. This is a technique developed by Dr. Beth Parker and provided through PACE Analytical, where an on-site lab comes and actually can test pieces of your core right on site and give you results from those. There were some bulk rock properties, and then we had some soil and groundwater results as well. So From this, there were several techniques used, good ones that we like for this investigation. There was a good initial conceptual site model developed, but the conclusions of these studies themselves said that we are not delineated vertically or laterally yet in terms of this contamination. So just to give us a little visual cue here as a shortcut, we're going to put a tracker in the bottom corner of this with our fundamentals, geology, hydrogeology, abbreviated as hydro, and biogeochemistry. And here it's just chemistry for brevity. And we're going to kind of walk through a simplified version of asking these questions about the site so we can see how it informs our approach. So keep an eye for that tracker. And after this initial one, like it's not a judgment call, the red, yellow, green, but because we're not delineated, we definitely aren't in the green category yet for some of these. So how did this inform our approach? What was our goal? We wanted to definitely characterize the geology at the site and then really work on that delineation of our plume here. We did that through focusing on the fractures with that high resolution discrete fracture network approach. So really focusing on the geometry and the hydraulic conditions of those fractures, the interconnectivity of them, because those fractures are what we determined were going to be the best pathway for contaminants to move through the site. And some of the things we did were just more locations. We had to step out laterally, deeper boreholes because we weren't delineated vertically, multiple downhole tests that we'll get into, and focusing really on that high resolution data collection, harkening back again to our fundamentals and our Bedrock matrix decision tool. And we chose to use hydrostratigraphic units as kind of a heuristic to help us characterize the site and kickstart our conceptual site model. So hydrostratigraphic units, or HSUs, because it's less of a tongue twister, are basically single fractures or groupings of fractures in close enough vertical proximity that they represent that one unit, one zone. They're usually separated by either unfractured rock or rock that has minor bedding plane joints with low transmissivity, so it's not affecting the hydraulics within the site. And groundwater flow within each of these HSUs should be distinct from the other ones. And we're going to walk through a little bit here about how to use our matrix guide and the questions within it to help us develop our hydrostratigraphic units, our HSUs. So this is a bit of a teaser here. We use integrated plots to layer data on top of more data to make sure we're bringing in these multiple lines of evidence here. So what you're going to see in the next couple of slides is us layering data on, and on the right-hand side of the slide, we're going to track which tools were used and keep track of how they help inform and improve our assessment based on that red, yellow, green quality designation. We're using one borehole just for a simplified approach. Generally, you need obviously multiple locations, multiple lines of evidence, and the tools that I'm going to go through are just one set of tools, and later Jim's going to talk about some additional ones. So this is an iterative process, both as you add in more tools and techniques, and also as you add in more locations. So again, this is a simplified version. This is what worked well for our site. You need to make sure when you're keeping this tool in mind that you are thinking of your specific site. So let's walk through some of these techniques here. So first off, we have really good core logs are the basis for our first look at geology here. You can see these core logs incorporate both descriptions of the rock itself, the lithology, and also fractures, faults, relative motion, vein fills, that sort of thing for these discontinuity descriptions. They also include useful information like penetration rate, PID readings, recovery, and rock quality designation, or RQD. And these paired with a great photo log are a wonderful first step for characterizing geology there in terms of actually getting to see what's described in the logs there. We took this a step further, and we were lucky enough to do a lot of geophysics at this site. Which includes our first one, which kind of goes in parallel with the core logs, the optical televiewer, or OTV, essentially a camera that goes downhole and takes an image of our borehole there. You can see around where the pointer is that there were some water clarity issues, and this camera does depend on the water being clear. So there are some unknowns with this specific tool, but that's why we're layering tools on top of each other here. So we have multiple lines of evidence to back things up. So we're going to add in some more tools, including the acoustic televiewer, or ATV. That's the yellow column you see there. We also have the caliper. In this case, it was an acoustic caliper, and the gamma. So you can see that the acoustic televiewer does not care about water quality. It can see those fractures because it's using travel time instead of just an optical lens. So you can see there are fractures deeper in there where that water quality was lower. The caliper is giving us information about where these fractures are open, average borehole diameter, if we're seeing anything where wall rock is falling off into the hole, highly fractured intervals like you see at the top of this image. And gamma is really wonderful, especially if you have a specific marker bed or package of beds, to find where you are within a formation, and you can help you correlate across the site if you have this, if you have this tool available to you. For us, we can see that it's a mixture of sandier and shalier intervals, but with these sets of tools, our geology is getting up to a green here. We feel very confident for this specific location that we've characterized the geology well. So we're going to add in some more tools to try and work on our hydrogeology and our biogeochemistry. Temperature and conductivity is a continuous probe run up and down this open borehole. Not a lot of interesting temperature readings within this specific location, but there is a conductivity peak there, or kick, in red. So maybe something's going on there in terms of flow. We also, in the geophysical suite of tools, have the heat pulse flow meter, HPFM, up there on the image. And this essentially, you section off different lengths of the borehole and isolate them, and then use heat as a tracer to see if there's any flow vertically within that section. So again, looking at shorter sections and then really working to see if there's any flow within there. The results from both these temperature and conductivity and heat pulse flow meters for this location weren't really compelling in terms of like anything exciting jumping out at us. So we took it a step further and added in another tool to try and get some better hydrogeology information. So we're again layering those tools. And this is the fluid replacement test that Jim described earlier. And I can say in the field, it's one of the most exciting tests because you get live data. So you can see these things happening in real time. And so you're going to see conductivity change on that x-axis again, like Jim showed. And there's a big peak here, big conductivity change associated with a fracture that we can see in our ATV. So we know there is flow coming into our hole from the formation at that fracture. So we're getting a better idea about our hydrogeology. And this, you can perform this under ambient conditions, and you can also then choose to do some pumping and stress the conditions a little bit there as well. So now we just need to work on improving our chemistry a bit and maybe our hydrogeology more. But this is that core DFN tool. This is an incredible technique, and it includes, this plot includes concentrations from both fracture surfaces and rock matrix. And you can see our peaks of different concentrations up toward the top of our borehole there. And it's important that you test both the fracture surfaces and the rock matrix, because that contamination within the porosity of the rock can be important when you're thinking about designing your remedy. So we're getting a better idea about chemistry now. And from these pieces that we've layered on, we can make some initial picks for our hydrostratigraphic units. Because remember, we're not just doing this for fun. We're actually working to develop these units to help inform our conceptual model for the site. So these were our picks, and that's with, a green, a yellow, and a yellow sort of qualitatively for how we're doing based on our assessment. But this is just one location. So if you add in more locations here, and we went through this process again, adjusting things up or down, looking for specific fracture sets or packages of different beds that you could track across the site, you're going to refine this and go back and improve them with the addition of more locations, but also with the addition of more tools, some of which that Jim is going to talk about next.
All right, thank you, Taylor. So yeah, as mentioned, this is an iterative approach, and it takes a lot of teamwork and a lot of real-time decisions. So that's where communication really does come into play in terms of quality. So what this looks like is a field geologist, talking with the project manager, talking with the office hydrogeologist, talking with the geochemist. We're all getting on conference calls. We're looking at data. We're sharing screens, and then we're making additional decisions on where to collect the next set of data. So here's an example of the stereo nuts that I had discussed before, as well as some rose diagrams and some dip angle histograms. And this is for fractures and for bedding planes. So now that we've had the geophysics run, we get this nice report, and we're able to get a better handle on what the dip angle of the fractures are and how that informs the rest of the geological component of our CSM. And so from there, we make another decision. Okay, where do we think our HSUs are? Let's go test those HSUs with packer testing. So packer testing is a technique where you lower on a drill string with a sampling port in between. You have two packers. Those packers inflate and isolate the fracture zone, as you can see here. We decided where the packers would be installed and which zone we were going to test based on all the other information that was layered upon other information. And, we went out and we did two packer tests. And in this case, you can get your total COC concentration from packer tests. You can also get hydraulic information. So now we're adding more information to our CSM, and you can see on the tracker down here, we've got more chemistry, we've got more hydro, and we're green across each one of our fundamentals. After we've done the packer tests, we need to make decisions about where to install a long-term monitoring network. As everyone's aware, for a site such as an environmental contaminant site, you need a long-term monitoring program. You need to see how your plume may or may not be moving, and you need to be able to demonstrate that your remedial action is actually doing what you think it's going to do. So in this case, we look at concentrations and we look at the purpose of this very specific well. One borehole may be have a different purpose than another borehole. In some cases, we might be trying to delineate below the plume, delineate vertically, so coming in underneath the plume and having low concentrations there. In other cases, we might be trying to delineate beyond the highest flow zone, but beyond the highest HSU, or in other cases, we may be trying to delineate side gradient. So we look at all that context, and again, we get together, talk about it over conference calls, and make decisions on where to install the screens. And a question that often comes up is, do you need to install screens or do you keep an open borehole? I think that's very site specific. It's mostly related to whether or not you're going to have borehole collapse. In that case, you probably do want a monitoring well. In this case, for this site, we were concerned about borehole collapse, so we did install monitoring wells. Ideally, if you have a very nice, competent bedrock with discrete fractures, you can work with open boreholes. That's generally better because you have access right to that fracture in short term and in long term. So after we install monitoring wells, then we can do more testing. We can do more hydraulic testing in particular. In this case, slug testing. We have our slug set up here for downhole testing. As you're probably aware, a slug test is where you put a slug of a solid slug, preferably, or pneumatic slug into a well, and you change the hydraulic head in the formation, and then you watch the recovery of that change in the formation. So on this case here, we have a plot of the results, and you can see dimensionless drawdown on the y-axis and dimensionless time on the x-axis, and this is the recovery of that slug, that pressure change, instantaneous pressure change in the aquifer. And you can see a nice recovery, very linear on this plot here, and a resulting hydraulic conductivity. So then we can also get more relevant biogeochemical information. Now we've installed our monitoring well network. We're able to sample those, with, let's say, a low flow sampling technique, and get sort of short-term and long-term CVOC concentrations for this case, where the site contaminants were chlorinated VOCs. We also want to collect general water quality parameters. The general water quality really plays into how that biogeochemical environment is reacting, how the general water quality might be affecting the microbiological consortium that's existing. In this case, we're looking for Dehallococoides and Dehalobacter as the known reductive dechlorinators of the chlorinated VOCs. So it goes beyond just what the chemistry of your contaminant is. You need essentially, even for monitored natural attenuation, if people are familiar with the three primary lines of evidence, your CVOCs, are they declining over time? That's a line of evidence. What's your water quality, your geochemical conditions? Are they reducing? Is your pH okay? And what's your microbial population? All those play into not only an active in situ remediation, such as bioremediation or chemical oxidation. It plays into long-term monitored natural attenuation as well, because you have to demonstrate your natural attenuation through these lines of evidence. So now that we've collected, essentially more data, we've come back to our HSUs, and now we're adding in the new chemistry data along the HSUs here. And so now we have good chemistry data and good general water quality data to help further detail this cross-section and the HSUs that we've previously identified. So in summary, this presentation, we went over a lot. Hopefully everyone stayed tuned in. But we discussed the development of a Bedrock matrix tool to assist in Bedrock characterization, how we've used that tool, particularly at a site, and what the development of that tool looked like. A few really key concepts that I think are good takeaways. The use of multiple tools for multiple lines of evidence is highly regarded in fractured characterization and discrete fractured network approaches. The high resolution data collection is preferable so that you can understand the details and really develop individual HSUs and characterize those separately and individually in order to provide efficient and cost-effective remediation. And the spatial distribution of data points for characterization of geology, hydrogeology, and geochemistry, those are all very relevant to what your purpose of your study is, where you are on your site, and what you're trying to achieve, not only from a big picture, but where are you going and what are you doing? That's how I think about it in terms of a scope, and also in terms of a project execution. We have different locations and we need certain information from those locations. All of this requires real-time dynamic decision processes, which takes a lot of management. You can ask Heather Budzik, our project manager, how much, coordinating there is between different teams, scheduling, making sure by the time we get the data, the technical team is ready to evaluate it. The rest of the team is ready to get together and talk about it and make decisions. And through all of that, going back to the core value moment, is effective and clear communication. And you need a multidisciplinary team. We have geologists, we have hydrogeologists, we have geochemists, we have engineers. All of those are contributors because we're thinking beyond just this one location. We're thinking, entire strategy, like site closure strategy. We need to characterize the site so we can remediate this site, so we can close the site. And with that, that's the end of the presentation. We'll open it up for questions now.
Yeah, thank you, Jim and Taylor. That was really a great presentation on fractured bedrock investigation and characterization. I know, having spent many years on fractured rock sites, it's great to have a tool like this to really kind of guide you through the process. So if anybody has any questions, you can either enter them in the chat or you can raise your hand to ask it live. I see there's already a few questions in the chat, so we'll start with those. So the first question is, for those outside of the state of New York, how can we best apply this matrix?
Yeah, I saw Matt started to answer this in chat, and Matt Krantz was one of the folks who helped develop this tool. But that third part, the matrix, is more generally applicable to different sites and different states. I think it's really it's useful to have those geology guides for people, but like New York State, we do have like a lot of sedimentary rock. It'd be really nice if you are trying to apply this to a different state or a different region. Like say you're in New England and you have a lot more hard rock, you're dealing with metamorphic fabrics that might affect things. Like you could customize those parts earlier. And I think Jim, you had something to.
Yeah, thanks. I was going to say pretty much the same thing. I'll add on that, having worked on many fractured rock sites here at Parsons in many different states, these are things that we do most of the time, if not all the time. If it's like a little phase 1 or something, and you're just trying to get a quick understanding of what's happening in bedrock. But most of our sites are really complicated, and the things that we're doing here is really sort of coalescing it and organizing it. And again, like the desktop component and the reference guides, it's a really great adaptation, and I'm really happy that we did it. You can also do that on your own project in your own state. It's really that desktop study of like, okay, where am I? What's the geology? What do I know about this regional situation?
Okay, I see Lucy Liu, you have your hand raised. If you can unmute yourself and ask your question, please go ahead.
Thank you, Jamie, for the presentation. I really enjoy it. So I'm not sure if I understand this Bedrock matrix tool correctly. Like, is this tool is actually kind of like collection of like regional information for either geology, hydrology, all the information put in this tool. Then when we come one site, we will use kind of those information as background information. Is that the tool does?
That's part of it. So there is a lot of that's like background information. That's like the kickoff point, but it's hard to actually visualize all the questions that get asked. But like, what techniques are you using to characterize like hydraulic conductivity at your site? Like, how well is the geology characterized, and what techniques have you used for that? Those are the questions in that sort of red, yellow, green part that you can ask about your site and see sort of like, have I used enough of these techniques? What else is a possibility for me to use, especially if you're not from as much of a technical background? It's just a way to help people understand qualitatively, like how well have we done at this site so far, and what options are there to improve our conceptual site model if we're not happy with the current characterization. I don't know, Jim, if you have something to add.
No, I thought that covered it very well. Thank you.
So I'm just wondering further to my question is like how we incorporate all those background information to the site, the scale. Usually those information going to be a large kind of regional large scale, but when we come to like a few hundred site, that's some very localized faults.
You got to zoom in. Yeah.
No, I get what you're saying, and what I think why I think it's relevant is, and how you apply it is, okay, you look for what the regional trends are in, let's say, the fracture network, and then as you start to collect your site specific fracture network, you kind of bounce that back to what the regional geology is. Or if you're in a unit, let's say, that does have a dissolved gypsum seam, you're going to look for that. You're going to try and understand where that is. That might be a marker bed, or any marker bed would be a good example. Okay, we know there's a marker bed within this sandstone. Let's look for that and tie it into our conceptual model so we know where we are in the stratigraphic column relative to the regional geology.
That makes sense. Thank you, Jamie. I just sorry to keep you longer here, but the further question I have is like, for the site to apply this tool, do you have a sense of like the budget for project? Because I think we're gonna need lots of information there. I would imagine it's gonna be a complex with.
That's a great question.
Much more budget.
That's a great and practical question.
I think that's going to be site specific, and we can work with individual teams on what data we have, how much more data we need, what's the purpose of the study,
what's the objective,
what's the end goal, and I'd be foolish to be able to just like rattle out a number.
Yeah.
No, I'm just like try to have a like initial guess, like, okay, if this project, let's say we have like millions order or like few K or something, like we should consider this.
I think
tool.
that's an interesting question. I guess you can prioritize certain techniques. Like the fluid replacement testing is really inexpensive relative to some of the other tests. So if you're like, we can't do geophysics at the site, like we can do fluid replacement. There's ways to layer things together to get to what you need within like the budget that you have for your project. And like you might not need every single tool at every single site, depending on how complex it is or what you already know about the site.
Okay, yeah, that makes sense. Thank you both.
Thank you. Great questions.
Mm-hmm.
Jess?
Yeah, so I see a few more questions in the chat from John Halstead. What's a reasonable open hole length to avoid cross-connecting fractures?
Well, that ties into another question about preventing inter-borehole flow. Depending on like the level of impacts, for example, if you're in a DNAPL source area, which I try not to even drill through, but if you're outside of it, and depending on your risk of receptors, you can leave borehole open for short periods, and that's what we did at the case study. We knew that the contamination was to a certain depth anyways, and even though we do have HSUs, there must be some communication through, which allowed the plume to go deeper. So the use of flute liners, which is that sort of sock that unrolls down into the borehole, that is how we use, that's the tool we used in between the drilling and the geophysics and the bore fluid replacement testing and the well installation. So there's a mitigative tool to reduce the amount of fracture connectivity. And then if you have, let's say a water supply system at a certain depth, you'd want to avoid, interconnecting that. But again, it's a good question, John. I don't know that I have a rule of thumb because I think it would depend on that specific, the specific borehole and the specific site.
Mm-hmm. I think when we are thinking about making those HSUs or like defining the HSUs, you are trying to think about like, can we put in different wells like effectively here in these? Are they too close together? Do we like, should this be considered one or two HSUs? And that's why it's nice to have those multiple lines of evidence to help you make that determination.
And there's one other question from John. Can air hammer be used for some holes?
Yes. Yeah, I like the core so that I can identify the fractures and look at the core. But for example, a site where I had good information, that one that I showed the picture of the dissolved gypsum seam, I knew right where that fracture was. That was where it was contaminated. We didn't even need to drill deeper than that. And when we went to remediation, where we had to put in a lot more pilot tests, wells, and a lot more drilling, the time it takes to core in this rock, and John, you know the same rock in Canada, but it's probably a factor of 10 between coring and air hammer. So eventually I just went right to air hammer, just blew down the hole, got 2 feet below the fracture. If I wanted to, at that point, I even phased out regular geophysics, and that we just self-performed fracture aperture or borehole aperture, because again, at that point, I was confident in the aperture test was really something that we could self-perform, and we didn't need to bring in, a geophysicist team for $10,000 mob charge and $5,000 a day. So I hope that answers your question.
Yeah, it looks like you guys have already answered a lot of the other questions in the chat that have similar questions. The one other unique one is from Chris Johnson. Didn't catch a mention of dye tracer tests and in-well point velocity probes as diagnostic tools. Realizing that all fractured bedrock sites are unique and generally complex, is there a hierarchy of useful diagnostic tools?
I think that's one of the sort of like next steps. This was like the tool was essentially just meant to make it more accessible to like especially regulators and site managers right now. But I think it's sort of in the back of every geologist's mind of like what tools are best used, like in certain cases, like, and what's most important. And that is, again, site specific. I feel like, Jim, you're going to have something to add.
Yeah, no, those are good tools as well, Chris. We didn't include them in this project, so we kind of didn't include them in this presentation. I think they're very relevant, and it's a good idea to come up with a hierarchy of tools.
I think we'll take one last question. If anyone else has more questions after this, please just reach out to Jim and Taylor directly. Their emails are up here. So last question from Michelle Patterson. How do you handle weathered bedrock zones? Some weathered bedrock is so weathered and incompetent that in the past we treat it as a soil layer. Do you use any additional techniques to characterize this and whether it should be characterized as bedrock instead?
Yeah, these are great questions. That's the hardest question to answer, I think, out of all of these. So luckily in Western New York, where I've worked a lot, glaciers scraped off the soil and we have a pretty distinct top of rock, not so fractured. We've also worked in Virginia where, there were no glaciers, or, well, not glaciers in the last 20,000 years. And, it's Appalachia and it's just saprolite. And saprolite is basically a gradation across 50 feet from soil to rock. That project was very challenging trying to identify what top of rock even was because it varied based on the level of weathering. So I think the approach that we mostly talked about here was getting into rock and getting below that top of rock zone. Top of rock, fractured top of rock zone could almost be a presentation in and of itself. And how do you differentiate between a well that's pretty much finish on top of rock, and then you have 2 feet or 3 feet or 5 feet of weathered top of rock. So a lot of the same tools can be applied, but you got to really worry more about your borehole staying open if you are trying to apply them. So I think it's a matter of identifying where you can start with your top of rock, with your bedrock approach, and then, deal with the top of rock sort of as its own unit. I think that's usually the best approach, is to try and, depending on the level of weathering and the thickness, the top of rock is a challenge and can oftentimes just be its own unit, essentially.
Okay, with that, I think we'll wrap up for today. Like I said, if anyone has any other questions we didn't get to, or if you think of them later, please reach out to Jim and Taylor directly. So a link to the PDH form was posted in the chat. If you had any issues accessing that and you want to get PDH credit, please reach out to us and we'll get that to you. Likewise, if you missed any of the questions or the answers to them for that PDH form, the recording of this webinar will be up on our YouTube channel in the next few days. If we can go to the next slide. So our next webinar will be on February 14th on navigating the surge, real-time strategies for the imminent electrification demand. This will be presented by John Daly at the same time as today, 12:30 to 1:30 p.m. Eastern. And just as a little bit of context, in 2023, Parsons acquired IP Keys, a provider of cyber and operational security for hundreds of utilities for electric, water, and gas across North America. And he'll be speaking on the topic in February. So thank you to everybody who joined us for today's webinar, and we hope to see you again in February.